Hello everyone. My name is Jacob Creedon. I'm a software engineer. I work at a biotech company. I work on machines that synthesize RNA and DNA. And in my free time, I like to work on little audio and video projects. I'm playing around with Rust on microcontrollers. So this talk is embedded with Rust using the Rust programming language on microcontrollers. First off, why not C++? C++ it's unsafe by default. I mean, working with raw pointers is dangerous, and it's very easy to make mistakes and introduce a whole wide variety of bug classes. And there exists tooling to kind of help protect you, but usually there's static analysis tools that are very expensive, proprietary, kind of what's happened in the community is, it's prompted development of new systems programming languages, Go by Google, D, Rust from Mozilla, what this has got people asking is should I be starting a new code base in C++? And more people are saying, you know what, no. We need to use something a little more modern, a little more safe. But that got me asking the question, well, is that also true for embedded? Embedded is kind of a special use case. So with Rust, maybe. The other two kind of rely on garbage collection, which is kind of a non-starter for embedded work. Rust is a new systems language with one of its main goals being safety. It has unique features, ownership, borrowing, lifetimes that allow it to be free of data races, and also eliminates the need for garbage collection. It has very modern ergonomics. It's very to use from a development environment standpoint. A lot of that owing to Cargo. It's the package manager and build system. Let's give it a go. I picked a little project to kind of help figure this out. I'm building a little MIDI controller. I do live sound events, and so sometimes it's just nice to have a little bit of extra control service to work. So let's first start by trying to get a blinking light. Then let's get go on to something more real, like getting fader readings. So first we'll pick a hardware platform. I just picked F3 Discovery board, pretty standard dev board from ST. Not very expensive. Onboard debugger. Next, let's get the toolchain up and running. It's pretty simple. Rustup.rs. Rustup is a toolchain manager. You just download it, install it, run it. You pick the nightly toolchain. Features needed for embedded development aren't yet in stable, but don't let it not being stable trick you. Nightly is pretty stable all on its own. It's just Rust has a pretty good ethos about guaranteeing API stability, and so there are some APIs that they don't want to guarantee until they've actually worked out all the kinks.
I think as of 1.25 that may have changed like 6 weeks ago.
Yes and no. There's a little more nuance to that, but we also need, ironically, GCC. Really, we don't need the compiler, we just need GDB. And then GDB server is needed. OpenOCD is what I'm using with the onboard ST-Link. you know, JLink, Blackmagic Probe, whatever floats your boat. And then as far as editors' IDEs, I'm sure lots of you are Vim and Emacs, you know, aficionados, but if you're in the IDE space, Visual Studio Code has a good plugin, as well as IntelliJ IDEA. Yeah. So we've got our tooling set up, but before we jump into the code, let's take a few minutes to talk about the ecosystem. Like I was saying, Rust has a package manager and build tool. It's called Cargo. It installs packages that are called crates. And it just works. It's very similar to NPM or Yarn if you're in the Node, if you've done stuff with Node.js. And yeah, just it downloads and builds the dependencies along with your project. And so as far as the crates go, the community is kind of settling on dividing out functionality into different layers of abstraction. And we'll just kind of quickly go through that. First we've got our architecture crate. This is just bindings to registers that are common to a given architecture. So, you know, with for example, Cortex-M, you've got a lot of common peripherals that you're going to see that are the same across all vendors. Systic, ITM, you know, just kind of all the NVIC, all of your standard, you know, stuff, you know, is available through an architecture crate. If you had a different architecture, you know, that you'd have a different crate providing, you know, those peripherals. Next is a device crate, or sometimes called a chip support crate. You know, this is for registers specific to the chip and its peripherals. You know, so your analog digital converters, timers, etc. And usually these crates are 90% auto-generated. Vendors usually provide what's called an SVD, which is a document that basically lists out what are all the peripherals, what are the registers, what are the bit fields within those registers, you know, and what you know values those are. Those can have. And so next we've got the HAL, hardware abstraction layer. This is meant to be a abstraction on top of common device peripherals, and it's meant to provide a consistent interface for things like SPI, I2C, Serial, GPIO, I'm going to use the Arduino example, but like Arduino is a terrible HAL if you've ever tried to port it to other platforms. But you know, when you load up Arduino and you say, you know, pin mode or digital write, you know, what's happening is underneath, you know, someone else has done the work of abstracting, okay, what does digital write mean? You know, oh, it means, you know, flipping this bit on this one register. This is you know, and if you've ever looked under the horrors of the Arduino source code, they don't do it very well, and there's a lot of like baked-in AVR, you know, assumptions. They've done it, I think, quite the right way, and it makes things like implementing drivers a lot easier. You know, so a driver crate is for external components that you know, like an accelerometer. You know, so you know, for example, on the F3, they give you an accelerometer. It's on I2C. Its bindings only talk to a generic HAL interface, and so you know, all you need to do is swap out what's underneath, you know, and you've got a generic driver that's portable, you know, across different devices and platforms, which is really handy. Finally, there are board support crates. These are, there's a little bit of implementation to them, but they are more just kind of a meta crate, a collection of other crates for targeting a specific development board. You know, so, you know, once again, for the example, you know, with the F3 development board, you know, it kind of automatically will pull, you know, what's the correct architecture device, and HAL crate to target, you know, code for this board. There aren't very many of these out there right now, but for the ones that are around, it's very useful for getting up and running quick. So speaking of which, let's get up and running real quick. That doesn't really come through on the projector very well. That's a full example of a blinking light, but let's take a look at it piece by piece. First thing we do is our imports, kind of like what we were talking about. You know, we have an architecture crate and our board support crate. And then in here, inside that, we're pulling out all the other things we need, the device, you know, the HAL. Then we do our initialization. Up at the top, we're getting our Cortex peripherals. That's from our architecture. STM peripherals. That's from the device. We then kind of pick out individual peripherals that we need. You know, and so in this case, we just need the flash, the reset, and the GPIO controllers. And then we basically stuff those references into our abstractions. And so, so we've got, for example, a delay abstraction. You know, that's just taking our Cortex systic, and turning it into a simple timer for our delay. You know, our LEDs, are coming from the GPIO. And then these new objects that we've created here kind of exists as our way of controlling the microcontroller. And so the main loop is pretty simple. There's 8 LEDs on this board. We're just going to turn on the first one. We turn it on. We wait half a second. Turn it off. Wait half a second. We've got Blinky. And so I tried to embed video. It's a nightmare. You're going to have to settle with this fake stop motion. It works, I promise. You can come bug me later if you really want to see it. Yeah, last step, build, flash, and debug. All you need to do to build is cargo build, which is incredible if you've ever had to deal with CMake. And all the little things you've got to twiddle, it just works, which is nice. We start up in the background our GDB server, and then it's just standard GDB. It's our remote target. We load and run. Yeah. Okay, so moving on to something maybe a little more complicated. We've got our blinking LED. And that was a very simple example, and it was all that functionality was covered by the HAL. You're not always going to have a HAL for the functionality you're using for. HAL is meant to cover kind of the basic things. Chips generally have very specific peripherals that are not as easy to abstract, and so let's kind of go over how do we write and read registers without the HAL? So for the let's try and read a value from a slider. Setting up an ADC on this particular chip is a lot of work and it's very boring. So I'm just going to pick one register as an example. But I mean, it's basically the same pattern. We take the peripheral from our device crate, and then we just modify it. And so, just kind of walking through the syntax. This is our peripheral ADC1. Configuration CFGR configuration. That's a register within that peripheral. We say we modify it. And in here, the syntax is we're jumping into a closure. If you know what a closure is, great. If you don't worry about it. It's just, we're basically coming up with a list of commands that will get executed atomically. In this case, kill myself while I do this. This is a 32-bit register. It has various bits. So, for example, I'm setting the alignment bit and I'm just clearing it. The continuous bit, I'm clearing that because I only want a single sample. And then I want it to overwrite. So I set that bit, and I mean, these, like I said, these are all auto-generated, so they have meaningful names that match what's in ST's reference manual, so it's pretty easy to follow along. And then, so here's an example from the main loop. You know, we set the start bit, we do a busy wait. Reading is pretty much the same as writing. You just dot read, you know, and then what bit within that register you want to read. So we're going to busy wait for the AD to complete the conversion. You know, we get that value from the register. We clear our status bits. We print it out. We wait half a second, and then so here on the here on the right is example output from that. Okay, so yeah, we've got analog values being read, working proof of concept. That's kind of it for examples that I've got to present. This is kind of where I am right now on my project. We've now upgraded to a new dev board, 4 motorized faders, MIDI input output, moved to a 1-bitsy, smaller, easy to use. Peter, yep, is here in the audience right now. Yeah. So what have we learned? We figured out how do we set up the tool chain, what is Cargo and the Crate ecosystem as it exists now, and how to utilize that ecosystem. We've learned how to read and write registers. Overall, I think, like to our earlier question, I think the answer is yes, we can use Rust for embedded. You know, let's talk about why not. You know, there's the biggest thing is it's not quite yet stable. Breaking changes happen every once in a while, and it ends up being a little bit of a yak to shave because once every 2 weeks you kind of have to go through and get everything to hit the new API. Even just yesterday, you know, I pulled a project I hadn't touched in a couple of weeks, tried to build it, and it doesn't work on the latest Nightly compiler anymore. And it was a simple fix, but you know, if you let it sit for a month, you know, or 2 months, you know, the number of changes you needed to make kind of pile up, and it's more work than it's worth sometimes. Yeah. The other thing is examples are limited, and you know, whatever is available is often outdated because the breaking changes. Ecosystem, and then finally the ecosystem is young. Right now it leans heavily towards Cortex-M, and then within that heavily towards STM32. Lots of people love STM parts, so that's not usually too big of a deal, but you know, if you're a Freescale fan or you know, something else, like there's a lot more work you just have to do on your own rather than just downloading and using a crate. The last thing I'll say, right now I feel like Rust on microcontrollers is best if you have a lot to gain from its safety features. If you're doing very simple things where you're not touching a heap, you're not having to manipulate raw pointers in C. You know, C is still good enough. It's better to use the language you know than to try and jump into Rust because, oh, it's the hip new thing. So yeah. That being said, there's a lot to look forward to. Embedded is hitting Rust stable this year. A lot of those features are stabilizing, there are still, I think, a couple things that are not in the stable compiler, but once that hits, kind of the ecosystem is ready to lock down and say, okay, this is it, we're done, or not done, but we're in a good spot. Let's start devoting more resources to it. AVR support is coming soon. Rust is based on LLVM, so basically anything with an LLVM backend is supported by Rust. Right now what that means is in the embedded world, that's just Cortex-M and MSP 430. AVR support's coming soon. There's talk about RISC-V as well, but there's not very much RISC-V chips out, so not a huge thing. And then documentation is really starting to take off. People are doing a good job at pitching in. So thank you. And I had planned for questions, but I don't know that we really have time. So you're welcome to come find me during lunch. I'll probably have boards out and we can talk shop about whatever. So thanks.